This is the next video in the series on acid-base titrations. In the last video, we talked about calculating the pH at various points in the titration curve for a strong acid and strong base system. And in this video, we're going to talk about the different important features of a weak, strong titration curve. And that will work for weak acid, strong base systems, and also for weak base, strong acid type systems. Okay, so here's our titration curve, like we did on the page with the 4 curves. We can tell that we have a weak acid on the left and a strong base on the right. So we know this is going to be a base. Use it as the titrant. We can tell from the high pH here that this is going to be a strong base, and from the low pH here and the flat part in the middle that this is going to be a weak base. That's how we can identify it. And the important parts of this curve are going to look very similar to the strong acid, strong base, but some of them have different names than on the last one. So we still have the initial point. That one is still important. We still have the equivalence point here in the steepest vertical section. And remember when we drew the weak curves in the last one, we also indicated a third point, which was halfway between the initial and the equivalence, right in the middle of that flat region. And that one's called the midpoint. So we care about those 3 points, and then we can also label our left half and our right half of the curve. So our left half of the curve, we said, was where we had a weak acid in the majority. So we're going to call this the weak acid or the buffer region, because weak acid-base systems can form buffers. And then on this half, we have our strong base, and it looks just like the one in the last problem with the strong acid, strong base. So we're going to call it the same thing, strong base region. So this time there are 3 points and 2 regions of interest. And the problem solving is going to look a little bit different this time because we have a weak acid in the system. So we'll start with the initial point. So at the initial point, we have not added any base titrants. All we have is weak acid. But we know for a weak acid, it's not as simple as plugging the molarity into the pH formula. We need to do an ice table first. So we'll need the pKa of the acid to find how much it dissociated. And once we find how much it dissociated into hydronium, we can take the negative log of that hydronium concentration to find the pH. So it's still pretty simple, but you have to do an ice table before you find the pH. Okay, the next region is called the buffer region. And that is the region where we have more weak acid than we have strong base. So it's our left half, where we've only added a little bit of titrant so far. So in this case, in order to know which part of the region we're in, we need to find the number of moles of each. And we should find that we have more moles of the weak acid than we do of the weak base. And that means we need to neutralize all of the strong base that we've added, and we neutralize using a DNA table or a stoichiometry table, where the N is for neutralize. And then we reach the end and we find the number of moles after the neutralization happens. And then, because we're in the buffer region, we're going to use our new favorite tool, the Henderson-Hasselbalch equation for buffers. And technically, the Henderson-Hasselbalch equation has molarity and not moles, but because the volume of these two things is the same because they're mixed together, we can just stick with moles. And the Henderson-Hasselbalch equation will give us the pH. And I'm also going to add an asterisk here. Technically, not this entire region is the buffer region. A little bit at the beginning and a little bit at the very end before the equivalence point is not technically in the buffer region. Remember that if it's in the buffer region, the ratio of the weak acid to the strong base in the solution needs to be between 10 and 1/10. Or in other words, the pH of the solution needs to be between the pKa plus 1 and the pKa minus 1. So there's a slight region at the beginning and the end where the pH is not within this region, and there would be a different way of solving it, but we are not going to talk about that in this video. So we've got initial, we've got buffer region. In the middle of the buffer region is the midpoint. And we'll add that one here because it has a slightly easier way of solving. The midpoint is where the amount of strong base that we've added equals 1/2 the amount of weak acid that we had in our titrant flask. So in order to know that it was your midpoint, you would have found the moles first. So you find your moles, you discover that one of them equals 1/2 of the other one, and that you're at the midpoint. And if you're at the midpoint, that means your pH equals your pKa. You could also do something similar if you wanted to use the buffer region formula. Since technically the midpoint is in the buffer region, this buffer region step series would still work. You could find the moles, use your DNA table to do the neutralization, and plug those numbers into Henderson-Hesselbach to give you pH. But if you're smart and you're sneaky and you realize that the titrant is 1/2 of the total, you can skip straight to the pH without doing all the work. All right, so our next region is our equivalence point. The equivalence point is where the amount of weak acid is equal to the number of moles of strong base. But unlike the last video, just because we have an equal number of moles of acid and base doesn't mean that the pH is going to equal 7. Because when the weak acid is neutralized, it forms its conjugate pair, a weak base. So we always start by finding number of moles, and that should tell us when we have the same number of moles of the two pieces that we're at the equivalence point. We'll do our DNA table to neutralize those two, and then we'll take the numbers that come out of them and solve for the molarity. We should only have molarity of weak base at this time. All the strong base should be used up. All the weak acid should be used up and transformed into weak base. And when we have the weak base, and we want to find the pH, we know we have to do an ice table. Just like we had to do here at the initial point. So we do our ice table, we find our concentration of hydroxide made by that strong base, use that number to find hydroxide concentration and to find the POH, and then we use the POH to find the pH. So fortunately, even though there's a weak part of the system, we don't have to do an ice table all of the time. We only have to do it at the initial point and at the equivalence point. At these other points, we can use the Henderson-Hesselbach equation because we're in the buffer region. Okay, and our last region is going to be the strong base region. And that's where there's more strong base than there is weak acid. See if we can fit it here at the bottom of the page. Okay, so the first thing we always do is define the moles of each, because finding the moles is how we know which region we're in. So we find that there are more moles of strong base than weak acid. So we do a neutralization. We do our DNA table, and we should find that all of the weak acid is neutralized to weak base, and there is still some strong base left over. We find the molarity of that leftover strong base. And at this point, technically we have strong base and we have weak base in solution, but the pH is much more dependent on the strong base because it dissociates completely. So we can just assume the only relevant piece of information is the strong base. And so we can skip straight to finding the pOH without doing the ice table, just assuming the strong piece is the only piece that matters, and then find the pH. Okay, so let's review. We have the initial point where we had to do an ice table before finding the pH. We have the buffer region where we have to do a Henderson-Hasselbalch equation. We have the midpoint at the very center of the buffer region where we can either do a Henderson-Hasselbalch or we can skip straight to pH equals pKa. At our equivalence point, the process is a little bit more lengthy. We have to do a DNA table and an ice table before we can find the pH. And over here in the strong base region, we can assume that all of the strong base that's left overrules the weak base that's left and use a DNA table to find the pH. So these steps are a little bit different than the strong acid, strong base system, and definitely a little bit more difficult. If you were solving the opposite way, if you had a weak base and a strong acid, this process would be almost entirely the same. Some of these times when you take the pH and times when you find the pOH are flipped because you have a weak base, but otherwise the process is almost entirely the same. So those are your general problem-solving strategies for finding the pH at different points during a weak, strong titration curve.